That will go there very quickly. Yeah, except AI tools.
Hello.
Left.
So this way?
Yeah, then you can see the metrics, right? They
Okay. I think we can get started as people slowly come in. Hello, everyone. Welcome to the final day of CoLLAs 2025. So we are starting today with an exciting keynote talk by Andras Gyorgy. So Andras is a senior staff research scientist at Google DeepMind London, UK. He received his PhD from the Budapest University of Technology and Economics in Hungary. He held research positions at the Institute for Computer Science and Control, Hungary, leading the machine learning research group, and at the University of Alberta, Canada. He was also a faculty member at the Department of Electrical and Electronic Engineering, Imperial College, London, UK. So his research interests include machine learning, statistical learning theory, online learning, optimization, and more recently, large language models. Andras is going to talk about non-stationarity, online learning, and loss of plasticity. Thank you.
Thanks very much. Thanks for the invitation. So first, I would just like to make a security announcement. This room is dangerous if there are more than 235 people here. So we are in luck. Okay, so yeah, so I'm a learning theorist by training, and I worked in the past, I don't know, 20 years on online learning. And I found that actually there is a huge connection between online learning and continual learning, which is kind of, not really taken into account in research. So basically these two communities exist in parallel, and there's a lot of things in theory, a lot of things it's like continual learning is mostly experimental, and the same kind of ideas are developed mostly independently. There are some papers which cross-pollinate and use some algorithms from here or some analysis from there, but mostly this is missing. And I thought that it would be good to think about this more. And basically the work I'm going to present is about loss of plasticity and using the insights I basically have from online learning. Okay, so well, as it's at the last talk and last morning, so I will show some formulas because that's how we can go to theory, but I try to limit them. So basically, sequential decision making, that's the more general way for online learning. It's typically it's set in a convex optimization setting. I will connect this to continual learning in a moment. And then, so basically there's a decision maker who will receive a sequence of loss function, and every time step it needs to make some prediction and suffer some loss. And the nice thing in online learning is that there is no assumption on the sequence of loss functions, other than most of the cases they are convex, but sometimes we can go beyond that. So this is the benefit of this formulation. So just to make this a bit less abstract, because I said that there are some loss functions, but you can think of it that there is this loss which is obtained by some linear predictions. Like every time step you see some data and then you compute the loss function from this data. But for the sake of theory, you don't need to actually look at this connection ever. You can just think about that there are loss functions you want to optimize. Yeah, and the performance measure in online learning is usually regret, which means that we measure the performance over the whole horizon. Like every time step you make a prediction, you also suffer a loss. So this is in contrast to the normal learning, where you just get a bunch of data and then you have to train your predictor on that. And in the end, you get a predictor and you evaluate the performance of this predictor. So this is more constrained in the sense that while learning, you still have to perform. But the nice thing is that you can use this regret to actually upper bound the performance of the final predictor. And typically the kind of bound we get is that on average you suffer 1/√T loss, which is the same thing as what you would get in normal batch learning. Okay. Now, where it really connects, maybe one thing here. So there exists algorithms which will achieve this regret. So the regret is usually in a cumulative sense, so it's √T instead of 1/√T. So the nice thing is that there are algorithms where this bound is true for basically any sequence of loss functions. And here, so what is the regret? The regret is comparing the performance of our predictor to the best predictor in hindsight for the sequence. Like it goes a little bit beyond normal, statistical learning where you assume that there's a stochastic model and then this would be like the model parameter. Like here you see some realization and then you compute the optimal predictor for that. But the nice thing is that you just care what the optimum is and there's no other assumption. But and people in online learning usually say that this is great because we make no assumptions, so like this is good for non-stationarity, but it's actually not true. Because if you think that our baseline is that we make the same prediction at every time step, which really means that we assume that there is a good predictor, right? Why else would we compare to that? So we assume that there's a good predictor over for the whole data set and we want to compete with that. Okay, but we can go beyond this and we can go in the non-stationary setting, and the non-stationary setting we can see that at every time step there is a different comparator. So that at time step, instead of some fixed thing, we just pick the best comparator for that time point. Obviously, competing with that one is hopeless, right? So that you have an arbitrary sequence and then every time step you can change the predictor in an arbitrary way, that's not gonna work. So typically what happens is, just one that in the stationary setting, we just pick this UT every time for the optimum. Okay, but what happens in a typical setting that we assume something about this UT. So that if UT is nice in some sense, then we can give some bound. And the algorithms usually take into account what we assume about UT. And one very typical assumption which will connect nicely to continual learning is that we think that this UT is piecewise stationary. So that we compare to one predictor for a while, and then we switch to another predictor for a while, and so on. And in that sense, the complexity of this UT sequence is really measured by how many times the sequence changes. So like here I'm comparing to the best predictor at every time step, but it's not necessary. You could define this number of switches for any sequence of UTs. And then the bound, what you get is is this visible? Okay, so the bound, what you get is instead of the square root T, we get the square root T times the number of segments, basically. So like it's kind of natural that for each segment you can be as good as if you actually figured out where the switch happens. And this is the performance on the average segment, more or less. And then there are other ways to measure complexity of UT, like how much UT shifts over time and some other things. I will briefly mention them. But the idea is that once you have some complexity metric for the comparator sequence, then usually you can, unless it's too complicated, usually you can design an algorithm which can compete nicely with that sequence. Okay, and now if you look at this, we can think of this as a sequence of tasks, right? So for every segment where we compare with the same UT, that's kind of one task. And then when you get to the next task, then you compare with a different UT, which is optimal for that task. So this non-stationary online learning really maps into this sequential task problem. The difference is that here there is no, warm-up samples that you can use at the beginning of the task, that here is your new sample and then you learn on that, and then we evaluate performance. But here you actually evaluate performance immediately from the beginning and also on the training data. The nice thing is that you don't need to know where the task boundaries are. Okay, so that's, so this is really something like task agnostic continual learning with S+1 task, where S was the number of switches. Okay, so that's the introduction I wanted to say about online learning. And then let's just go to loss of plasticity. That's the other topic I want to consider, and then I will join them at some point. So loss of plasticity in continual learning is that things are changing the data, and then we are not able to adapt to that, and there can be like two types of loss of plasticity usually, that you can even stop training, or training gets hard over time, or training is not so bad, but generalization is really bad. And obviously this is a problem when you do continual learning. And so in the continual learning literature, there are a bunch of experimental work about what can be the reasons behind a loss of plasticity and how to avoid it. These include like choice of optimizer, or changing the step size, or the number of optimization steps, or the regularization. And maybe what's most relevant to what I want to talk about is that oftentimes, like recently, there have been some papers which try to regularize towards the initialization properties of, or initialization of the network. And I think that's a great idea. But if we think about it a bit more, using the fundamentals and principles, then we can do better. Okay, now loss of plasticity is usually, the reason for that is usually people think about that is because of nonlinearities. Right, so that there are these deep neural networks, and then there are nonlinearities, and then the nonlinearities will create the problems. But what I'm arguing is that some parts of loss of plasticity, or some properties, can actually be examined in online linear prediction. Right, so like if you think about loss of plasticity as like full loss, so that you can do anything, then obviously this is not the case. But in the linear case, you can actually do something. So let's see what that is. So for this, I will introduce like a special framework of this sequential decision making I introduced before. So this is the prediction with expert advice. Just out of curiosity, that who knows what that is? Like the prediction of expert advice framework. Okay, so very few. Okay, and then I will explain properly. So the idea is that we have the experts, like I don't know, weather forecaster. Like you have the weather forecaster pages, and then you don't know which one is good. And at every time you can take a look of what they predict, and once you do it, then you can think about like which one was how good so far, and what you believe about them, and then create your own prediction. And the goal is to create a sequence of predictions using the advice of the experts, which is kind of as good as the best expert in hindsight. But it's a very powerful framework if you want to combine a few algorithms, or you want, instead of model selection, it's like you have a number of models, and then you can run them in parallel as an ensemble method. Then this is great. It's in my experience, it's always much better than model selection. Okay, so a bit more formal, that every time step we get some prediction, and then the predictor chooses a distribution basically over the experts. This will be the weight of the expert. And then depending on whether the predictions can be averaged or not, if the predictions can be averaged, then you just average the prediction of the experts using these weights. Or if not, then you can just randomly select something, and then on expectation, you get the same thing. Right? And then the predictor suffers a loss, and the loss is basically the average loss over the experts. Right? So each expert has a loss, LTI, the is expert, and then you just take the inner product. Like this is really linear prediction. Right? Okay. And so probably the most famous and well-known algorithm for this is the exponential weights algorithm, which is roughly the same, like it comes from Bayesian prediction with log probabilities, but if you replace the log loss with arbitrary loss and apply the same things, then you end up with this exponential weights algorithm. So what is the exponential weights algorithm? That we basically keep track of a weight, this WTI for expert I, and then when expert I suffers some loss LTI, then we do this exponential update on the weight of the expert. And then every time step when we make a prediction, we just make a normalized prediction with this. So like if we have a fixed learning rate theta, then this is really like WT at DI is really just the exponential of all the losses of the IS expert, negative and multiplied by eta. But right, so this is the exponential weights algorithm. It's very simple, and the nice thing is that if the losses are bounded, then we get the square root t log d regret for this algorithm. So with the number of experts, it scales really mildly, and then we get the usual square root t scaling. Okay, so that's great, but this is compared to the best fixed expert. Right, but we are interested in the non-stationary case, right? So we are interested in a case when there's a sequence of tasks, and then at every, like, for a while you have task 1, and then you have task 2, and so on. So instead of this, we want to in hindsight to show the benefit of hindsight. Okay, so what we want to do, we want to compete with this non-stationary sequence. And the change what is done, so just keep in mind that this was the update formula here, just the exponential update. And what happens is that if this is called the fixture algorithm, is that you take this exponential update, you do the normalization, and once you did the normalization, you mix this new normalized weight with some uniform distribution over all the experts. So it's kind of giving a little bit of benefit or trust to each expert at every time step. And the cool thing is that this simple change, it will give us the regret bound, which scales with the number of switches to the best expert. Right, so that if the best expert changes s times, then we get now a regret bound which scales with the number of different segments, number of stationary segments. Okay, and I think this is really cool. But if we don't do this, if we don't do this, then what happens is that we will suffer a big loss if the best expert changes. And why is that? That if I go back here, then what happens is that if you don't do this kind of regularization or mixing in the uniform distribution, then you can really saturate the weights, right? So that some weights could get like extremely small, and then it takes a lot of time for the algorithm to recover. Right? So basically this mixing in mixing in this way will stop it. in my view, this saturation of the weights, which will become very small, unlike very large in neural networks, and but it doesn't matter. It's kind of the loss of plasticity, right? So that once you have some weights which are extremely small, and you're doing these exponential updates, then you can't recover these weights, and that's exactly the same thing as loss of plasticity. It's like you can think of loss of plasticity. If you train forever, then eventually it will go away, but you just don't want to wait that long. And this captures the same idea. So I think that this is maybe the main point of what I want to say, that in online non-stationary optimization, this is exactly the same dilemma you have to face. Okay, so some thoughts about this exponential or fixture algorithm, which is kind of interesting, that this mixing in this uniform distribution, you can interpret this in many ways. One very cool interpretation is that basically at every time step, you start a new exponential weights algorithm and then you run it until now. Like at time step 1, you start 1 and it goes over the whole time period. At time step 2, you start 1, it goes over the whole time period, and so on. And then in this way, you will have an expert which kind of covers the last stationary period, right? And then you can put a meta algorithm, a similar exponential weights algorithm on top, and average these algorithms, so this ensemble, growing ensemble of algorithms, and that's the same algorithm with proper weighting. And there are a bunch of other algorithms which do the same thing, that they run some kind of a stationary online learning algorithm, and there is a meta algorithm put on top. Sometimes it's with some complications, but the high level idea is that you can run these algorithms and combine them in a clever way. Now the benefit of the fixture algorithm is that it gives us an implementation where we can only keep one algorithm, right? So like we don't need an ensemble. We can compute basically the ensemble in closed form, and that's a great advantage. So what can we get using this type of parallel algorithms? So like we run a bunch of algorithms, and there are different versions where each of them needs to query the gradient of the loss, or there are some others where the best ones, this word plus is the most recent and most adaptive algorithm, which just queries one gradient at every time step. So like that's kind of matches the normal continual learning way. And the nice thing is, so this regret, I mean, it looks ugly, but it's extremely adaptive. So I think about that it was previously like square root t times the number of switches. Okay, and here we have a bunch of other terms. Like each term is bounded by t, so like you can you can recover from this that square root st bound, but what we have here is that pt is now so this bound is for online convex optimization where not in the expert setting, but you have like real vectors. Okay, and this basically measures how much the comparator changes. Like if you have a slowly changing environment, then this is small. Okay, and there is this other term which measures how much the environment changes. So this is basically the change in the loss function. So if the loss function doesn't change much, then we can also capitalize on that. And finally, this last term is that if our optimal expert has a very small regret, like in normal batch learning, we have these small loss bounds that if the best method has a small loss, then we converge much faster, and it's the same thing here. So like I just wanted to show this, that this is like an extreme, it adapts to all the niceties you can have, but without actually knowing what they are. It's like that's the most important thing, that you don't know this, you don't know what sequence, comparator sequence you want to compete with. So like you don't know what this PT is, but you can still compete it. And you don't know how the losses will change, but you can still adapt. But if they change a lot, then you will change more in the algorithm. If they change less, then you won't. It's like, I think that's the benefit of all this. And so potential problems with the direct applications is that maybe when you train a neural network, maybe you don't see immediately how things change, and you have to run, I don't know, bigger step sizes for a while so that you see the benefit. But these algorithms would really like weigh down that. Like if you make something which is really bad, then it, I'm not sure how they would recover or not. And the other thing is that most of these very adaptive algorithms, they require ensembles, and that's a lot of computation. So that's definitely an issue. Now previously I was talking about, this expert setting, but like in neural net training or whatever, we are in the real vector case, right? So it makes sense to think about online convex optimization over some Euclidean space. And then one thing to think about is that the domain is a Euclidean ball. And in this case, we can just run projected gradient descent. Like you make a gradient step, if you go outside of the ball, then you project back. And this algorithm, without any change, it has a really good dynamic regret. So dynamic regret, which scales the square root t times basically the change in the comparator sequence. Like if the best comparator stays fixed, then this is 0. If it changes slowly, then this is small. And it scales with the diameter of the ball. Right? So in this case, we can say that gradient descent, you don't need to do anything, it will just adapt. But how fast it adapts, it really depends on the diameter. And you can think of this, that if the diameter is too large, so like compared to t or whatever appears here, then when you need to go from one end of the domain, like the parameter space, to the other end, and then although it's just d, but this d is enormous, and you won't see that. So this is again kind of loss of plasticity in the sense. But if you have a small domain, then the small domain will guarantee that small domain compared to the step size, really. So then what we can guarantee is that you move quickly within this domain. So that's the idea. And if we compare this to the fixed share algorithm, so what happened with the fixed share algorithm, that we selected distributions, and every distribution, like at every coordinate, it had a minimum value, right? This alpha over d, which we mixed in. And so if we look at the logit space, then in the logit space is, well, it's not a ball, it's a hypercube in that case, but we have a constrained logit space, and where actually the parameter lives, and here we have a constrained domain where the parameter lives, and if the domain is small enough compared to the step size, or compared to actually how you can move with the step size, then you will not have this loss of plasticity, but just the distance, even in a linear or the convex case, will give you kind of a loss of, or imply a loss of plasticity. Okay, and the constrained domain is kind of like L2 regularization, right? It's like if you think about the Lagrangian formulation, so basically the large ball corresponds to small regularization. So this already suggests that if you have a good enough L2 regularization and the problem is nice enough, that will take care of loss of plasticity. And one of the methods to address loss of plasticity is L2 regularization of weights. Okay, now Now this was over a constrained parameter space. Now usually we have an unconstrained parameter space, and here I just want to mention maybe one algorithm which we used recently in a NeurIPS paper, where basically you put a, it's like it once you are in the whole Euclidean space, then the natural thing is to put a Gaussian distribution over that, and then your parameter, like in a Bayesian sense, and your parameters follow some drifting Gaussian distribution, and you update this as you see more and more data. And what happens that if you just do this, then in the stationary case, like you have some optimal parameter. This is for some problem, but it doesn't matter. It's like you have this optimal parameter, and then your posterior just shrinks around this optimal parameter. Right? But then if we get into the non-stationary setting, and then somehow this the environment changes so that the previous optimal parameter moves there, right? Then we'll need to come from here to there, like kind of slowly updating the parameters, and it takes a lot of time. But if we do some similar idea as in the fixture algorithms, like we mix in somehow, the idea is that you mix in some kind of a nice distribution. So like, something like Gaussian around the center of the domain, right? Then you can get like this last thing where a prediction which is a green ball, it quickly contains the new parameter. Okay, and what happens is that's like with the Gaussians, you can't really mix two Gaussians, because then you get mixture of Gaussians and it gets complicated. So like you can do some approximation and get another Gaussian as an update. And then the update we kind of did, which comes from the Ornstein-Uhlenbeck process, is that there was this previous parameter theta, and then you mix it with this base distribution mu 0. And then you can see that this is kind of the same thing as the alpha was before. Here we changed gamma to 1 minus gamma, kind of. But to make this work, and also that's true for the fixture algorithm, like you can set the change rate at the alpha to some fixed value, and you get some minimax bounds which are good all the time. But if the world is actually much nicer, then you want to adapt. It's like you want to learn this change rate, and there was some work like early 2000s also in online learning of how to learn alpha, and then in this method, I don't want to discuss it too much. We kind of try to learn gamma, and learning gamma is similar to change detection. So like I think that's an ugly part of this algorithm in the sense that it requires hyperparameters and so on, and you need to tune them because there is noise, right? There is noise and change in the parameters. And so if the noise is large, then you can declare, if you're too greedy to declare changes, then you will just declare change when there's a noise, and then you lose all what you learned. And if the, it's like there is this trade-off between finding the change and the noise tolerance. Okay, but this algorithm is on some random label and permuted MNIST. It works pretty well. So like comparators are like hard reset algorithms and L2 regularization to initialization and shrink and perturb, so like all others. And then of course I'm showing pictures where our algorithm is the best. But it requires some parameter tuning, Sakar, and really like how many steps you actually do the estimation of the change rate. So that's very important. But if you can have a good change rate estimation, then this algorithm works really well. Okay, but the idea again, what was before that we try to make the algorithm not to fixate on something, but give weights to other stuff and regularize towards other things. Okay, so this is really my interpretation of how these algorithms work, is that they somehow try to restrict the parameter space, so that in this restricted space the expressivity is preserved, but also the parameters can move quickly with the learning algorithm within this space. Like, so here there are again trade-offs, like if you restrict your parameter space to be 1 point, right, then you can move quickly, very easily, right? From 1 point to the same point, it's always very quick, but the expressivity is bad. If you have a huge space, then we see all these problems what we saw before. But what really happens, like if this is the simplex with the fixture algorithm and then getting from one corner to the other, it takes a lot of time. Like you almost set your probabilities to 0 and then like exponentially updating it will take forever to overcome that. But if we restrict it to this smaller space, which could be also restricting the Euclidean space to a ball, then in this smaller space, the change is fast. So like high changes, it depends on your algorithm and learning rate and all this, but this is really what you want. It's like when you want to find loss of plasticity, then you should think, that's my opinion, you should think that you want to restrict the space, the parameter space, so that you can adapt quickly, but you don't lose too much by the restriction. Okay, and then if you think about this even more a little bit, then what happens is when you initialize these algorithms, like you start from a point which is really good, from where you can get quickly to any other points of the space. But what happens when we have this non-stationary learnings, like we have new tasks, then what we learned from the previous task, that's going to be the starting point of our new learning algorithm. Like the important thing is that we always need to have a parameter, what we estimate, which is good for learning, not just good for prediction, but also good for learning. Right? So this gives us a bit more guidance of how to restrict the parameter space, that we want to have parameters which are good initializers for our learning algorithm. Okay, and if we if we take this idea seriously, then and now go to really like learning neural networks again, just in the previous case, then let's just look at what good initializations are. So like we want to preserve gradient diversity. It's like we want to be able to adapt to any new gradient, and then like the typical initializations are that we want to have weight matrices whose Jacobians have singular values close to 1. Like that's the nicest thing. So they are actually well conditioned. Okay, and then yeah, I don't want to go over these formulas, but they just kind of show that controlling the singular values of the Jacobians, you can control it by controlling the singular values of the weight matrices. And this gives us the idea for our algorithm. And the problem is really that during training, the parameters grow. And they also grow at different rates. So you have typically in experiments, you have both the small and the large singular values grow, but the large grow much faster, and then you end up with really badly conditioned matrices, and then we get away from this good initialization idea. Right? So our idea here was that that we want to constrain, like we want to have well-conditioned weight matrices, and then it turns out that it was enough just to constrain. So like this is the new regularizer we are introducing, and the new regularizer we are introducing is that we just try to make the largest singular values be 1. Okay, and we would also want to control the small ones, but the small ones are growing anyways, so like we don't need to do it. And then the bias terms, they are just regularized in a normal way. So basically, this is the spectral regularization algorithm we came up with, and it's, I think it's a pretty cool algorithm. If I compare it to, for example, L2 regularization, like L2 regularization, it also controls the singular values. The difference is that this one only controls the largest one. So like if you want to learn in directions which are not in this space, then you can do it much more freely than with L2 regularization. And I think that this gives the benefit. And then, of course, you can complain that computing the singular values is computationally hard, but you can just do really approximate cheap calculations to do it, like one iteration of the power method in our case. And then if I so there are a bunch of experiments. I don't want to show them all, but basically this is some random label task, but I want to show here. Okay. I thought the screen was bigger. Anyway. From there it was much bigger, but these are still unreadable. Okay, what I wanted to show is that so this is the performance, and then this orange thing is R. So like it's usually on the top. It's not always on the top, but in all the algorithms or all the experiments we ran, it was among the best. So like it's very stable. But what I wanted to show is sorry. Yeah, it's how much the weights can change, and these are the unconstrained algorithms, and their weights change a lot, and they also were bad. And okay, maybe these are the singular values. Okay, just sorry. Like these are the singular values. If you don't really control the singular values, then they grow. If you do it like you have L2 regularization to initialization, etc., then you get small singular values, which is great. But if we look at this, how much actually the parameters change, then what we can see is that our algorithm usually changes more. So like it allows more changes in the parameter space. Okay, and then here are some other algorithms like label flipping and class incremental and pixel permutation problems, and then we see that our algorithm is usually on the top. So like it's very robust over all kind of problems. And then if we do it on some other problem, the DMC suit, then it's also better than the reset algorithm which was used there. It's a slight criticism about the original reset paper that if you see this curve, then at the very end they just get better. If you perturb the parameters of the problem a little bit, then we get something like this, that our algorithm gets better. Okay, so basically what happens with this spectral regularization algorithm, that it's very robust, it's competitive with the best algorithms, and it's based on this intuition. Maybe it's an exaggeration, and you could get to the same intuition not just from online learning. It's like I'm not claiming that this is the only view, but it comes from online learning and first principles. Like if you think about like other algorithms, like L2 regularization to initialization. Like regularization to initialization is kind of the same idea, but it has that, oh, you randomly selected something at the beginning. Why regularize to that? Why not regularize to what you really want? Right. So I think that considering these insights, what you can get from these online learning algorithms which care about theory, although they are much simpler, that they can still be helpful. And so finally, I want to close quickly with the results of our paper with Claire Lyle and others, which was just presented yesterday. Like it's mostly Claire's work, and which connects loss of plasticity and primacy bias and grokking together, and that's related to the learning rate tuning, which learning rate tuning is also related to the adaptive algorithms in online learning. So what are these things? So loss of plasticity, we know. Primacy bias is that we start learning on some task, we end up somewhere, and then although if we learn further, then we can have a good training accuracy in the new task, but we get a very bad test accuracy. It's kind of the loss of plasticity with the addition that the training is good. Okay, and there is this other problem, grokking. So grokking is a recently observed phenomenon that you can have problems where you have a really good training accuracy, like very quickly, and then you have extremely bad test accuracy for a long time. And but if you keep training longer, then eventually at some point the test accuracy will become good. Right? So okay, first thing is how this can happen, because if the training loss is 0, then why do we learn? But obviously the reason is that the loss is measured by like some 0-1 loss, but the training is done with log loss, with cross entropy. So even though it seems that there is no signal, then there is signal. And a typical problem for grokking is modular additions, like it's, I don't know, modulo 117 or something like that, I think, so that you add up two numbers and then you want to predict the result. And the setting is that you select, it's like here you have a data set of roughly 10,000, and then you train on some of these, and then you look at the generalization in the others. And then there is some nice theory paper which shows that in some cases, maybe it's for a simpler problem, but basically in one step you can get into 0 training error, one gradient step, and then you keep learning different features over time, and once you learned all the necessary features, then boom, you get a good generalization performance, but before that the generalization performance is bad. Okay, so the question here, what we analyzed is that if we can induce grokking, then maybe we can address the problem of primacy bias as well. And so there is this, folk wisdom that large learning rates at the beginning are good for training features. And as I said in this example, the issue with grokking was that how long it takes learning the features. And then in continual learning, the question is that, okay, we may want to have large learning rates, but eventually you want to have small learning rates to make learning proper. And you don't know when task changes. So like how can you make the learning rates large? And so with this grokking experiment, what we showed that if you can introduce this learning rate rewarming. So like at different points on time, you increase the learning rate and then you decrease it again. And then we can see in this modular arithmetic task that once we increase the learning rate, then the performance quickly goes up. And we can also see that the activation pattern changes when the learning rate goes up. Okay, and then if we apply the same thing to primacy bias, then we see kind of the same behavior. so that when we make the change in the learning rate, then the performance improves. So like this suggests that really the issue with primacy bias is that you have to learn new features in a way that you had to do it in the Gyorgy case. And finally, I want to mention that if you do this, it's like you don't know when to change the learning rate. So like one very naive idea is to do it cyclically, and then there are some issues that if you change it too many times, then you can get instabilities and so on. But by and large, even in this reinforcement learning problem, the cyclic learning rate just makes things just works. But if you want to avoid really the issues with the cycling, then you can stop cycling after a while. But it really depends on the problem. So like if the problem is really non-stationary for a long time, then you may want to keep it. But these other things are usually much simpler, and you do it a few times and then it works. Okay, so how does this connect to online learning? So like this word algorithm which I showed, which was able to adapt to all niceties of the problem. What that algorithm does is that it instantiates different learning algorithms with different learning rates, with basically a good coverage of some range of learning rates. And it uses some meta algorithm on top of this to really figure out which learning rate to use when. Like so maybe doing something like this could be useful here. It's not entirely clear. We haven't tried it yet, but I think that's maybe the next thing we should do. Okay, so in conclusion, what really the take-home message of my talk is that there is online learning, there is continual learning, and there should be more interaction between these two, like algorithmic ideas, analysis ideas, and maybe from the theory side, really the problem definitions. Like so that the problem is not that I have this benchmark and I'm better on this benchmark, but the problem can be formulated often in this regret way, even including forgetting and a bunch of other stuff. I haven't talked about it, but it's possible, I believe. And so I just encourage everyone, both like there are not so many theories here, but I also encourage the theorists to actually look at continual learning problems and see how things are applicable, and the other way around to at least know about what happened in the theory world and get some insights for that. All right, thanks, Ern.
Great talk. I actually have lots of questions, but I'm just gonna ask one specific question first. I'm really intrigued by the spectral regularization algorithm. It seems like a really nice idea. You said it was not so bad to compute. How did you actually compute the gradient through that spectral regularizer?
To be honest, I can't answer that question.
Fair.
That's the thing when you have the students implement the algorithm.
Okay, got it. Since I have the microphone, I'll ask one more question. For the experts algorithms, you are relying, of course, on these experts to be doing reasonable things. Are there any conditions on the experts themselves for all this theory? Like, could I have one of my experts could do anything? I can have an expert that switches between DDPG and then starts running PPO and then does anything. It doesn't matter. Okay.
The general condition is that the experts' predictions don't depend on what you do. So if the experts are autonomous and they do whatever they want to do, then it's all fine. But if they, it's like basically that's the main issue with applying this framework, especially in the bandit case and so on, that if you want to train these experts, then it's a question which experts should be trained on which data, right? And then if you navigate to some parts of a space where the expert wouldn't go, and then you train the expert on that data, that's problematic. Like if you just think about this what I said, that you can just start learning algorithms at every time point, that works. But if you want to do like remembering stuff, which means that you have some expert which is good on one segment and then it's later good on another segment and so on, then you really need to figure out which segments to put together. And so if you want to learn on these segments, then you will end up with way too many experts. If you just want to compete with experts, then got it.
I had a question about the Gaussian rule. I was wondering, does it have a similar interpretation where you have like, I don't know, a posterior that you're, well, at each point you're starting off a new Bayesian algorithm where you're sort of only starting to learn from that point, and then you're averaging over these many different posteriors, or could you do that as well in a different way?
No, but I think that it would work.
Okay, cool, thank you. If I could ask a quick other question about the spectral norm, what's the similarity between like Lipschitz regularized networks? Because I understand.
Lipschitz regularized.
Yeah, so they make the neural network Lipschitz by also regularizing the operator norm.
If you bring it Lipschitz, that means that you're. I mean, this does that, right? Because you constrain the largest eigenvalue, but it's not enough. Actually, right? Because you also need the smallest one. I mean, maybe in the Lipschitz case, it also works, but it's.
Okay, thank you.
Yeah, so one thing that I thought was really interesting about the online learning perspective is that often online learning algorithms, there's an interpretation of them as kind of balancing a plasticity stability trade-off, in the sense that you're basically saying, okay, like I'm not going to do as well as I possibly ever could on like this particular sort of distribution I'm seeing, because I think it might change soon and I want to be able to be flexible to that. Whereas I think often when we talk about plasticity and deep learning, we're basically ignoring the like plasticity stability trade-off and just saying there are certain things that break in networks, and we want to avoid those. So do you think that like there's things we can take from online learning that would help us deal more with this like plasticity stability trade-off perspective, as opposed to like the kind of things you get for free that just improve optimization more generally?
I mean, I think that my view is kind of the same, right? So that this restriction of the state space, that's kind of you want something where things are stable, but it's more than stable. So like directly stability. I mean, like instability would take you out of this space of feasible region where you actually want to stay. So maybe it would directly apply.
Okay, well, let's thank Andras once again.